Do forces really exist? Hi, my name is Eric Normand, and this is my podcast, the Eric Normand Podcast. I'm going to talk about software design and domain modeling, and I've been talking a lot about Newtonian mechanics, and so I've been thinking it's worth deconstructing that. It's a very amazing model. It's an amazing model that Newton came up with. It's got 3 equations and a handful of concepts defined in terms of one another. And it manages to unify phenomena that we see all around us. But also if we look through telescopes, it makes sense of the motion of planets and moons around planets and the sun. And it's quite amazing that these 3 equations can do that. Okay, but first I want to talk about my book, Grocking Simplicity. This just came in. Today is Tuesday as I record this. I got them on Saturday. That I was on vacation, and when I came home, there were 2 boxes full of them that were overnighted to me from Manning, from the publisher. They were at the printers, but Manning overnighted them to me. So thank you so much. It was so lovely to get this and to be able to hold it after more than 2 years of work on it, of hand laying out each page. Of course, the production department did a really nice job of making it nicer than I could design. But still, they managed to maintain my layout, even while making it lovelier. So, Manning, thank you so much. You did a great job. The book is all about functional programming, and it's a book about elementary functional programming. What is it? How do you do it? Those kinds of questions. For someone who has a couple years of experience, knows at least one programming language, but is kind of curious about functional programming and what it's all about. So if that's you, buy Grocking Simplicity. If that's not you, if you are more experienced in functional programming, this book won't teach you like functional programming probably, but it was written for you, because if you're anything like me and you're talking about functional programming and someone's like, what is that all about? Or maybe they've tried functional programming but they didn't have a good introduction to it, and so I always wanted to recommend them a book, and I couldn't find anything that wasn't too that wasn't oversimplifying things or too academic, overcomplicating things. And so I wrote this book for me and hopefully for you to be able to give to people or recommend to them that they read it as an introduction to functional programming. So yes, it's for you and it's for them. It's available at Manning. Right now you can buy it and get it in the mail. Soon it'll be available on Amazon if you prefer that. But there it is, Grocking Simplicity. It's got a rabbit on the cover, rabbit professor teaching a class, because it's a grokking book. Great. Okay, let's get back to the topic. So, does a force really exist? I think the short answer is no. There's no such thing in the real world. as a force. Force is an abstraction that, it's almost mystical. If you haven't, kind of grown up with the idea of force, a physical force, it's a mystical idea. It at least it borders on it. It's an abstraction that somehow unifies a bunch of different phenomena. So a push, if I push an object, that is two forces, right? I push something, it's me pushing against the object and the object pushing back, resisting the push, right? So that's an opposite force. So a push is two forces. We often say a force, it's like a push. No, a push is two. Push is two forces. Forces come in pairs, right? That's the second law. Or is it the third law? Equal and opposite reaction. It just means the forces come in pairs. So there's a push can be a force, but so is gravity. And a push requires contact, but gravity does not. Gravity happens over a distance. So it's different. You got magnetism. Magnetism can be modeled as a force. So can strong electrostatic charges. These things can be forces. And what's really amazing about this concept of force is that they can all be modeled in exactly the same way. And it leads to stuff like what are called free body diagrams, which is what you use in physics class to, you draw some boxes and stuff, and then you draw arrows representing the different forces. So you have one for gravity pulling on the box, and then one for the person pushing on the box this way, and you can model a situation in terms of objects with mass and forces acting on them, and they move around. What's the velocity of this thing given, or what's the acceleration of this thing given all these forces on it? And that is a pretty cool idea. So there's stuff that we can learn about this idea of force, this abstraction, an invention by Newton. So for one, it ignores, like any abstraction, it ignores details, right? It doesn't talk about it doesn't need a source to be similar to other forces, right? So some forces are due to contact, some are due to gravitation, others are due to magnetism, some are pushes, some are pulls. There's really nothing relating these things, except in this model you can say, well, we can just draw an arrow. It's just a vector in 3 space. And so we've boiled down these very distinct phenomena into a number, or 3 numbers. It's a vector. So it's got 3 components, X, Y, and Z. So we've boiled this thing down into something very very abstract, very general. We've created that's really what I'm trying to get at, is it's abstract enough that it is now a general purpose thing that we don't even need to know what the force is from. We can just draw the arrow and say, oh, here's a force on this object. Done. You don't need to know anything else. Was the force due to a push? It doesn't matter. It doesn't matter. Was it gravity? It doesn't matter. So I think that that's actually a very important idea in this domain modeling, that we need to be able to, these abstractions create these abstraction barriers, and we need to be able to set aside, after we've drawn this diagram with all these arrows, we need to be able to set aside, where do these forces come from? It doesn't matter. At this point, it doesn't matter. We've already accounted for all of them. They're all on the diagram. Now we're just going to add up these vectors, right? Okay, so that's important lesson number 1. Lesson number 2, I think, is a little bit easier to dismiss. But I think if you... Okay, no, let me put it this way. I can imagine if you went back in time to him presenting at a conference at the Royal Society, this model, someone would raise their hand and they would say, but what is a force? What exactly is it? Can you point to one? Can you explain it to me? And I hear this all the time when people are talking about new concepts in programming. People always ask me, what is a monad? What is it? It's like, it's just a mathematical construct, right? It's just a thing that has these functions, right? That has is a functor. You start just naming things, right? And people want to have a concrete thing that they can point to and say, well, this is a monad and this one isn't, right? And I think at some point your abstractions can reach such a generality that there's nothing anymore to point to. It's just a vector with this kinds of units, right? It's not. There's nothing more I can say because it's just a feature of the model. It doesn't exist in the real world. So I don't know, Newton was a very mystical person. He was into mysticism. And I wonder if that didn't play some part in him being able to, I don't know, imagine things that aren't real. I wonder if that didn't help him, deal with this problem of abstraction. That once you get abstract enough, mathematicians do it all the time, but a physicist abstracting, it might be actually kind of hard, right? And this might have helped him. So I think that lesson, the lesson there is that you might have to invent ideas that do not seem to have anything real behind them, anything you can point to, but they simply exist in order to make the model function, right? In order for, you could sum up the mass times the acceleration, right? F equals ma, or the sum of forces equals the mass times the acceleration. But so you can say, well, there's definitely something mass times acceleration, but what is it, right? Well, you can find it by summing all of these things that we're going to call forces. But what, they're all different and all different kinds, and you kind of have to know it when you see it. What's a force? Yeah, I don't know. I feel like this is an important thing, is that when you're building a model, you often have to invent something, and part of the challenge will be that it might be indistinguishable from something else you invented that is not useful, that is not helpful to the model, or that has all these problems. You want to keep your thing real and concrete, and sometimes you just need to build something general and abstract and unreal. Let's put it that way. And it's easy once you start doing that to go astray, to go wrong. And so you need some kind of grounding, right? Luckily, in a program, it might, like, your forces might just be an array of somehow you use the type system if it has one, or you use some kind of system to say, I'm going to just get the direction and magnitude of all these different things that kind of look similar, like they all implement the same interface, and I'm going to sum them up because they all have, they're just vectors of what we now call force, but it's newtons, and that's the unit. I'm just going to sum them up, and we'll see what happens, And look, when I do that, actually I get this other neat result. If I divide the mass out, I get the acceleration. This is the thing that Newton didn't have. This is lesson 3. Newton didn't have computers. He couldn't build the model, right? He had to imagine it, and he could never see it working. Whereas we could build a Newtonian physics simulator, like orbiting planets or billiard balls bouncing off of each other, something like that. That's totally based on his physics, his mechanics and kinematics. We could build that and see it work, and yes, that does look like how billiard balls might work, or this does look how planets orbit each other. And he couldn't do that. So we do have a check that he didn't have, right? We do have the ability to go, front to back, from observing the world, developing a model, to simulating that model and watching it and seeing, that actually looks like, could look nothing like the real world, or it does look like what we see in the real world. So that's the third lesson, is to use the modern amenities. That maybe we can do better. Not spend 1,000 years building big ball of mud, spaghetti code model, and just get straight to the good one. All right. This has been my thought on software design and domain modeling. My name is Eric Normand. You should get my book, Grocking Simplicity. It is out. It is ready for you to read. All you have to do is enter in a credit card number on Manning's site, and it will be delivered to your home, and you can read it. Yay. Please read it. Let me know what you think. If you like this episode, you should subscribe. There are more like it and more coming. And tell your friends if you like it. Also, I appreciate ratings and reviews because that helps other people find it. All right. Like I said, my name is Eric Normand, and as always, rock on.